So we continue with our discussion on the application of heat transfer theories, and I think today I would like to wind up that discussion. So before I move on to the final topics, I would like to make one correction to the equation that I wrote last time. If you remember, I was considering the melting of a sphere, and I wrote an equation which describes the temperature field within the spherical object, and I also wrote a set of one initial condition and two boundary condition for this at t is equal to 0, at t greater than 0, and as I said that r varying between 0. And this r, the radius is changing as a function of time because the object is shrinking as melting is progressing. And then we have t everywhere is ti or t0. These are our standard notations actually. Initial temperature field is, uniform initial temperature field is always denoted by this. And t greater than 0 at r is equal to 0, which of course is the center of the sphere. So this is submarginal liquid where it is undergoing melting, and this is the bulk liquid which has a temperature of T sub bulk, and this is the melting temperature of T sub mp. R is equal to 0, so we have minus k, and at R is equal to RT, which hitherto is not known, we can say that we have, as I indicated, that T could be is equal to T sub mp, or we can say that the flux is equal to H times T bulk minus T mp. That represents the heat flux. So this is what I had written, and I also said that we cannot solve this equation as such because the statement is not yet complete, because it appears that there are two unknowns here. One is the temperature field and the other is the radius itself, and for that I wrote this equation. So this source term actually I copied from the previous discussion when I was talking about the heat transfer or the phase transformation in a solid, that is the wear rod cooling problem. But there I added this term, if you remember, if you look at the notes, you'll find this was added to the governing equation of heat transfer itself. So that was rho Cp. So that was plus rho delta H. So how the fraction changes, austenite is a phase fraction actually, any one of the phase fractions. So that is the equation I wrote for wear cooling problem. And I inadvertently did a mistake by putting in this term here without realizing that these are all watt plus watt by meter square. This is also watt by meter square. On the other hand, these are all watt per meter cube. This is watt per meter cube. And this term has a dimension, if you check, it is watt per meter cube. Okay? So this is not right actually. The correct expression here is, so that I urge you to correct in your notes. And then you see that this is what it is. This is kg per meter cube, and this is joules per kg, and this is meters per second, and that gives us joules per meter square, because this meter will cancel out, and that becomes is equal to watt per meter square. So now it becomes dimensionally consistent. With gamma s, it is consistent dimensionally with this governing heat flow equation, but with radius of the sphere, it becomes consistent with this head flux. So now this is the equation, boundary condition, initial condition here is at t is equal to 0, we have r is equal to r0, which is the radius of the initial radius of the sphere, or we can say r0 or an ri, I would say, or ri, which is known to us. So now I have a complete statement. I have, it's a conduction, convection, combined conduction convection problem. So I have, this is the second equation and this is the first equation. These are the set of initial and boundary condition to the first equation, and this is the initial condition applied to the second. So they are to be solved together in order to predict the evolution of temperature field within the solid, and as a result of which we will be able to find out the rate of melting. And this necessitates that the heat transfer coefficient is known to us, and the actual process actually is a little bit more complex because of the more fact that when a cold object is projected into a solid, typically what happens, a solid shell forms. The shell could be thick or thin, and the shell remelting could take place very quickly, but nonetheless, if you plot the radius, typically in a pure melting problem, we will see that the radius will continuously decrease as a function of time and it becomes 0. This is without any shell formation, but typically when you project a metallic object into another metallic solution, what happens is from this initial, if this represents the initial radius, then what happens from here, the radius actually increases and then it goes like this. So this time essentially represents a critical time by which the original, so the radius, as you can see here, the radius increases as a function of time. This is the Ri value, and this is the radius increases because the shell forms and the shell grows, and this shell attains, this diameter attains a maximum value, and then the shell remelting starts, and at this particular point, at this particular time, now the original solid is exposed to the surrounding, and henceforth the melting proceeds exactly as it becomes a pure melting problem. Okay? So this is a solid with shell, and this is no shell. And what is this shell? This shell is this. And this, what is the composition of the shell? This is the bulk material which has solidified. And how much, what would be the size of this shell? This also can be predicted from the same equation itself, same set of equations, by changing the initial and the boundary, changing the boundary conditions, and this thickness of the shell will depend on what is the thermophysical properties of this solid, what is the superheat, okay, and what is particularly the thermal conductivity of the material. So the superheat is an important parameter, and thermophysical properties. Plus the size of the sphere. These three parameters determine that what should be the thickness of the shell which is produced on the wall of the solid itself. And we must understand that there may be a contact thermal resistance, because there are two dissimilar metals at this particular interface, okay, which is a solid-solid interface nonetheless. This is a solid, but this is a solid of the parent material, and this is solid of the bulk material, so there may be an interfacial resistance also. All sorts of complexities can be addressed provided you know the physics involved in the whole process itself. So let us, with this correction and a little bit of discussion left from the previous class, let me now tell a little bit about the solidification also, solidification process, and so solidification basically, as you all know, involves heat transfer. So we extract heat from the liquid, and as a result of which what happens, the temperature of the liquid goes down, and once it starts to go below the liquidus temperature, then the solid formation starts, and once the solidus temperature is reached, everything becomes solid. And from the solidus temperature itself, the temperature can further go down, the casting can cool while it is within the mold itself or outside the mold, and as a result of which the continuously the temperature would decrease. So in solidification problem, typically superheat is first removed, and once superheat is removed, superheat means the heat that is above the liquidus temperature, heat corresponding to that delta T which differentiates the liquidus temperature and actually temperature of the solid. So MCP delta T represents the superheat. So it removes the superheat first, and once the superheat is removed, then the solidification process starts. And once solidification is complete, then solid cooling stage. So superheat removal basically takes place in the liquid state itself. There is no phase change involved. Heat is being extracted, but still the material is in a liquid phase. Then there comes a temperature region in which the metal stays or the material stays both in the liquid and the solid phase, and that is when the temperature is typically bounded by, for an alloy say, is greater than solidus and less than liquidus, and that is the regime in which an alloy would appear in both liquid and solid state. Of course, for pure metal, the metal freezes at one single temperature, but nonetheless for alloy, this is the characteristics in which we will have a liquid solid region existing. And once, so to the temperature, when it is greater than T liquidus, we have liquid phase. This is liquid plus solid phase, and then when T is less than T solidus, then we have, it is only solid phase. So as the temperature goes down, we have phase changes which is taking place. So the heat transfer coupled with phase transformation is a characteristics of the solidification process. But then how it is different from the process, wire cooling process, where also we have seen austenite to perlite phase transformation, but that was within the solid, it was completely heat conduction. But in this case, what is going to happen in this phase, it is a pure convection problem. Okay, there's a liquid phase. From liquid, the heat is being transferred to the mold wall, and from the mold wall, the heat is being extracted to the bulk. Between this temperature range, we have both solid and liquid which is present in the system. So it's a conjugate domain basically, and it's a very complex kind of a scenario here because we have a lot of microstructural changes which takes place during the solidification process itself. So it's a pure convection problem, and because you have solids and liquid, so we'll have the features of both conduction and convection process, and as far as heat transfer is concerned. And in the final stage, it will be again, this phase is akin to the problem that we have discussed for furnace cooling or wire cooling problem. So this part, it's already explained that how we can formulate the cooling of a solid and how we can address the temperature field. But this requires knowledge of the flow to tackle. So not only the heat transfer is important here, but the fluid flow controls the heat transfer phenomena. So it's a conjugate problem of fluid flow and heat transfer. Both are involved here. And as a result of which the subject is really complex. It is not possible to formulate based on whatever we have learned so far, that we can take a solidification problem and then formulate it. But I wanted to give you some idea that one part of the problem is relatively simple, which falls in the same framework which we have discussed so far. But the first phase of the problem, when the molten metal starts losing heat from its initial pouring temperature till it becomes completely solidified, the problem is relatively complex, and it necessitates that we address fluid flow and heat transfer processes simultaneously. Those of you who will study solidification process later on, in some other courses, they will maybe have a chance to see, particularly a course concerned with the modeling of solidification process, then what are the equations of flow, what are the equations of heat transfer, etc., how the solid-liquid interface is treated. All these complexities can be addressed, but which I think is beyond the scope of the current course, and here I think it is sufficient for us to note that this part will require extensive knowledge of fluid flow and heat transfer and their coupling, and that we can do, fluid flow heat transfer in the presence of phase transformation, because there is a solid to liquid, liquid to solid conversion, and that itself is associated with an enormous heat effect. So the fluid flow and heat transfer are going to be mutually interrelated, and that brings in further complexity. It's a nonlinear problem, coupled problem, and it is multidimensional. There are two different solids and phases, and their interfacial contact resistances. So you name a complexity and it is there. So dealing that, beyond what I am discussing here is perhaps not desirable. Now, one important aspect I just want to address, that when solidification takes place, so suppose if you have a mold here, and you can see that when the molten metal solidifies, for example, then what happens is that you pour molten metal, and then as a function of time the solidification takes place. So basically the surface becomes solid first, okay, and then the solid front keeps on moving, because the solid movement of the solid front, as we all know, is opposite to the direction of heat extraction. So that is, heat is extracted from the mold to the outside. So therefore we can say that the solidification front is going to grow in this particular direction. So the center is going to be solid later, and the periphery is going to be, the surface of the ingot is going to be solidifying faster. In the process of solidification, we also know from our fundamentals that the shrinkage takes place, okay. So the mold, which is initially at room temperature, or maybe sometimes preheated barely up to 100 degrees centigrade or so, into which when you pour molten metal, which may be at 700, 800, 1000 or 1600 degrees centigrade, as solidification commences, the mold expands because of the heat, continuous increase in the mold temperature itself, and the casting shrinks, and as a result of which what happens is a gap between the two is created. This is what it is, and this gap typically can be, if you do not add any mold powder, in that case this can be expected to be filled with air, and we all know air is a very poor conductor of heat. So the air, presence of any air because of the shrinkage will retard or impede the rate of heat flow, and as a result of which the solidification could be delayed. So typically what we do, we add mold powders which are low melting point oxides, basically oxides of silica mixed with some alumina, and when they form compounds, the melting point undergoes depression. So various kinds of oxides are there in different proportions, mostly silica, alumina and calcium oxides, okay, iron oxide sometimes also, potassium oxide, sodium oxide, etc. And when you pour this low melting point oxides, what happens? They fill the gap, and as a result, and displaces the air. So as a result of which what we see, that we have a mold surface here, then you have a solidifying casting here, and this is filled with now my liquid mold powder. That we all know from our knowledge of solidification processes, that the liquid mold powder will improve the surface finish, absorb the inclusion, and so on and so forth. But from the heat transfer perspective, the most important part here is that this liquid film, okay, which is the result of the melting of the mold powder, okay. So this really replaces the air, and as a result of which facilitates the transfer of heat. In the absence of any mold powder, this would have been filled with atmospheric air, which has a very poor thermal conductivity. So liquid mold powder not only increases the surface improvement, provides surface improvement, but also facilitates the transport of heat. Now suppose you have, the interest here is you will not be able to, because so then what happens is that you have heat flow from the mold, from the casting. So this is my casting here, this is the casting, so which is solid. From the casting the heat flows here, and then it flows through the film, and then it flows through the mold to the outside temperature. So that's how, so we have several resistances, and the film resistances needs to be known also in order to perform, that at what rate the mold is receiving heat, at what rate the heat is being lost from the mold surface, and so on. So if you want to perform any calculation, in that case it becomes a necessary input, because this determines the rate of heat loss from the ingot itself. And I will just show you that, because I was not able to discuss this part in this course. So at least one single application of the heat transfer theory, perhaps to find out that what is the thermal resistance due to the film, that can be explained to you with the aid of a simple example. Let us consider a cylindrical ingot and a casting in a cylindrical mold. This could be a cylindrical bloom in continuous casting, or this could be a cylindrical ingot as such. Now, if we have the ingot which looks like this, then obviously I am doing an exaggerated figure. Okay, so I will have this is the hatched part is my ingot. So I write it ingot, and this is the yellow part which is my mold wall. So mold has a finite thickness. If it is an ingot casting process, you will know that the molds are as big as the ingot itself, because whatever heat is being lost by the solidifying ingot is mostly absorbed by the mold. Okay? So if the ingot could be 10 ton, the mold could also be weighing about 9 ton, 10 ton or 11 ton, which essentially tells that the temperature of the mold material can go as high to 700, 800 degrees centigrade in practice. So whatever is here in this gap, that is the liquid mold powder or liquid film. Suppose the ingot is a tall ingot. So at any point around the center of the ingot, which would show something like a one-dimensional behavior, this is the kind of a scenario that can be depicted. Now let us say that this is there are three characteristic temperatures here: the ingot surface temperature, mold inner surface temperature, and mold outer surface temperature. If we say that this is T outer and this is T ingot inner, okay, and this I would say therefore T mold outer. Okay. So then I can say that from the heat transfer theory we can write down that the heat flux from the governing equation to be is equal to T I minus T m 0, and this is going to be ln. If this distance is R0 and this is RO, okay, this is RO, so therefore R outer and this is R inner. We must, although I have shown it in a very pronounced scale, we must understand this film thickness could be few micrometers only, okay, few microns only. So basically, therefore, dimension wise this Ri is exactly equal to the inner diameter of the inner radius of the ingot itself, because the film is not as thick as I have depicted in the figure itself. So I can say that this is ln Ri R outer by R, and this R represents the radial coordinates. So, and this equation we have done it in one of the assignments. Okay, so we can calculate. So this basically is the flux, and if you do it like this, then if your flux is So, if you want to define a thermal resistance, the thermal resistance becomes this. As I said, flux with respect to flux. There are two possibilities, as I have indicated. If you do this, then what happens? Thermal conductivity is watt per meter Kelvin, and this is, we have R is in meter. So, if you do it like this, then you get thermal resistance is equal to meter square Kelvin by watt. That is what it is. If you say this is the thermal resistance. On the other hand, this R is the radial coordinate at any R, because flux is inversely proportional to R, that we all know from the governing equation. So, the conduction, principles of conduction heat transfer is being applied here, and this is going to be not complete. The thermal resistance is because of the film also. And this is. So, there are two thermal resistances. One is the when heat flows from inside, from here to here, it experiences the film thickness as well as it experiences resistance due to the thickness of the ingot, and this is the solid resistance offered by the thickness of the solid ingot. That is what it is, and this is our thermal film, which is the resistance offered by the film, which is created by the gap which exists between the solidifying ingot and the expanding mold itself. On the other hand, if you want to do it in terms of this, then we have Q is equal to Q times area. If you want to do, then you have, so we will write it like this, then it is better. QA, so that is equal to TII TMO divided by, okay, the RR will cancel out, and this is going to be ln R0 by Ri into 2 pi Lk, where K represents the thermal conductivity and L is the length of, because the area comes into the picture, so that area is going to be 2 pi Lr, that is the, and then R and R will cancel out, and then this is going to be the thermal resistance of the film prime, because they have different units, and that is why I have represented. And in this case, the thermal resistance will have a unit of meter square will go, and it is going to be Kelvin per watt. So, you have two different conventions. Some people write resistance with respect to flux, some people write with respect to the net flow of this, but I think this is more appropriate, because it is not the flux, it is the, if you, because this is brought, this is represented by considering similarity between the electrical or current flow in an electrical circuit. So, here the heat flows, and so this is the quantity which flows, and this represents the flux itself. So, we know that therefore, this, as I said, that this parameter is going to be needed in order to do any heat transfer studies related with the solidification process itself. Okay? This parameter is known to us if you do a simple analysis, okay? Because R0 Ri is known, length of the cylinder is known. This is a simplistic approach, because it is a multidimensional phenomenon, it is more complex. Okay? But if you consider it to be heat to be most radially flowing, in that case this is the thermal resistance offered by the ingot. This parameter is known. This is known only at the instant when, for example, because this is the inner temperature, I have no way to access it. It is only when at the instant the mold is stripped, in that case the ingot is exposed, and that time only I can find out a temperature. Or on the other hand, one has to have a thermocouple inserted inside the mold by drilling holes, and then which will be touching the surface and measuring the temperature itself. So, this is again measured at the outside. This can also be measured or inferred at the moment when the ingot is stripped. This can be calculated, and now if you want to do Q, for example, what you can find out, that if you know the temperature, as I said, if this temperature is known, the outer temperature, because the temperature is going to be very high, so the radiation flux will prevail. So we can say that the Q, or multiplied by area, which is equal to Q multiplied by 2 pi R outer into L, and then we can say that we can write down this particular expression. So this Q is now, because the temperature is high, so we can say that this Q is equal to sigma epsilon theta s to the power 4 minus theta a to the power theta a to the power 4, radiation fluxes. So what I'm trying to show here, that you can determine this parameter provided everything else is known to you. That is the whole thing, because you have one equation. So as I have indicated, that this term, this is known to us, this is known to us, this can be measured, okay, in the industry, and this can, therefore, by equating the flux with the net radiation which is taking place from the ingot surface, the heat which is being lost, because the temperature here is going to be 700, 800 or 600 degrees centigrade. This of course is going to be time dependent, but at the instant of mold, at the instant when it is withdrawn, at that particular instant, if you have a fixed temperature, so we should have a fixed heat flux, and we can find out this, which will correspond to the resistance offered by the film at the instant when the ingot is being stripped. Now, it is also possible, mold is being stripped, it is also possible to find out, because this expansion of the mold and the contraction of the ingot, they can be exactly found out by knowing the coefficient of linear expansion and contraction of the material. Okay? So therefore, this space can be calculated, and if you know the thermal conductivity of the material, in that case you should be able to find out that if this is the dimension of this is known, and if you know the thermal conductivity of the powder or the liquid material which has molten here, in that case you should also be able to find out that what is the resistance offered by it. But the process I just wanted to say that a rough estimate of the thermal resistance offered by the film can be calculated by making certain measurements on the mold itself, and this can be used in order to calculate the rate of heat flow, the complete solidification time, and so on and so forth. But it is not so simple, because I have considered a one-dimensional scenario, and we must also understand that the powder, there would be a powder resistance due to the powder, and there would be a contact resistance. For example, because the ingot surface is going to be relatively higher temperature than the mold surface, so the temperature here is going to be substantially higher than the temperature here. So you can expect that the liquid is going to be, the powder is going to be forming a liquid film over here, and as you will go from here to here, possibly we will see crystallization of the film. Okay? So the film characteristics are not uniform within this space. The film characteristics will change. It will be liquid, close to in contact with the solidifying ingot, but it is like to be solid in the case of its contact with the mold wall itself. And there, because this is typically the powders are designed in such a way that they have good wettability characteristics. So if it is wettable, it wets the surface of the ingot very nicely, then we can assume that there is no contact resistance. But in this particular case, there is going to be a contact resistance, because at this particular surface, the powder is appearing as a crystalline phase or as a solid powder itself. So there may be certain amount of contact. So we can say that within this also, apart from the fact that I have used a one-dimensional approximation, within the here also we can have a powder resistance. One part of the resistance could be because of the solid resistance, the other part could be because of the liquid resistance, and finally we can have a contact resistance. So the film resistance that I am going to measure on the basis of this will actually fundamentally consist of several thermal resistances working in series, mostly the liquid film plus the solid film and the contact resistance. And how do you isolate them? That is a different subject that I don't wish to discuss. I just want to, for curiosity's sake, I just want to tell you that in one set of experiments we have measured, for example, the thermal resistance contact resistance we have measured, and that I want to just briefly say to complete the discussion here. So, if you remember that I talked about a ladle and a shroud and a tan dish, that the molten steel gets transferred from one vessel when I was talking on continuous casting. Okay. So, and this is, as I had also indicated, if you remember, this is like a ceramic tube. Now, if you look at this tube, so the fluid flows, so this is the thickness of the shroud. So, I am drawing one figure, center line, so this is an exaggerated figure. This is ladle shroud, and this is the center line of the shroud, and through which the molten metal flows from the ladle to the tan dish. And then we have the molds here, material is transferred. Now, when the molten metal flows here, basically we have a turbulent flow, so the flow profile looks something like this. Okay? So that knowledge also we have. So in this case, what is going to happen is that, so we have a bulk temperature or the center line temperature, which is say as a T bulk, or one can say T center line. This is going to be more or less uniform up to the wall, because near the wall, first is we are going to have a thermal boundary layer resistance. Okay? Then following the thermal boundary layer resistance, we will have, because this is a refractory surface, this is a liquid, so there is a refractory metal contact, and then we have the cylinder. So therefore, the wall or the thickness, the cross section here is, we have, if you draw it like this, then we can say that that is the cross section. So in here, so you can say that this is the shroud wall thickness actually. So we have from the bulk, there is no thermal resistance, it is more or less homogeneous because there is extensive amount of turbulence here. Come close to the wall because there is a thermal boundary layer, so there is a boundary layer resistance. After the boundary layer, there is a contact resistance, and then following that there is a shroud wall resistance. So that is the net rate of heat flow. So we can now say that Q is equal to the bulk temperature minus the shroud surface temperature, which is this temperature here, okay, T sub S, and then we can say that this is going to be equal to three different, first is ln R shroud outer by R shroud inner, and this is going to be 2 times pi L into K, as per our previous, where L represents the length of the shroud, K is the thermal conductivity of the material, shroud material, and then we have a contact thermal resistance, R thermal contact, and then we have a heat, if you know the boundary layer heat transfer, then one can show that this resistance is equal to H into 2 pi L into R0. That is what it is. I will now erase this is redundant. Okay. So this is and so the overall drop in temperature from the central line to the wall, and there are 3 different resistances as I have explained: resistance due to the shroud wall, resistance due to the contact between liquid metal, and resistance due to the thermal boundary layer. Now everything is known. If you know the H, this is also known. Similarly, if you know the thermal conductivity and length of the shroud, this parameter is also known. So I can say this is known to us. This is known, provided H is known. H can be obtained from a pipe flow problem. We know that Nusselt's number is equal to Reynolds number and Prandtl number correlations. So force convective correlation, if we know the Reynolds number, because we know at what rate steel is flowing, the velocity is known to us, or the throughput rate, so we should be able to find out the velocity, we know steel's property, and then we should be able to find out the heat transfer coefficient. Once we find the heat transfer coefficient, this resistance can be easily calculated. So therefore, if somehow we can measure Q, we should be able to find out that what is the thermal contact resistance, whether the contact resistance is low or high, or what is the exact value, that can be found out. Now, so therefore, by measuring the temperature at different location, the entire shroud actually is not visible in the industry because of the logistics. So at least about, the shroud typically is about 1.25, 1.3 meters, which is like 4 feet. So I would say about 2.5 feet is visible. So you can measure the temperature, which is more or less plus minus 50 degrees. This shroud wall temperature is always approximately about 900 degrees centigrade, which essentially tells us that flux is going to be the radiation fluxes. So if you take this to be the radiation flux, which is corresponding to the shroud temperature in the absolute scale multiplied by the external surface area, then this, by measuring the temperature, the flux or the net rate of heat transport can be calculated, and that will allow us to measure the thermal contact resistance. And this can be now used in the study of finding out that if that is what is the drop in temperature as molten metal flows from here to here. Okay, so this we went to the industry actually, and then we put some pyrometers here, and with the radiation pyrometer we measured the temperature here, we calculated the heat flux, we calculated the corresponding net rate of heat flow, substituted in this expression with all the dimensions and heat transfer coefficients, and found out the thermal contact resistance. And these contact resistances will form now a useful input in the study of further heat transfer in the liquid metal flow from ladle to tun dish. So even though I could not elaborately discuss the solidification, the equations corresponding to solidification, particularly in the case of when you have both combined fluid flow and heat transfer, at least I have told you about the intricacies of heat transfer phenomena in terms of solidification, that we have different regions. First is liquid, then is liquid plus solid, and then is the solid phases. And so it is a reasonably complex problem, not so amenable to formulation over the blackboard, but nonetheless one important aspect of the solidification process, industrial solidification process, which is concerned with the thermal contact resistance, for example, I have shown it in the context of particularly ingot casting, that how one can calculate. The principle remains same, that if you want to evaluate the thermal contact resistance, you have to know the temperature, you have to know the property, and one more parameter, that is the net rate of heat flow. Then you will have one equation, one unknown, and you should be able to determine. And this has been a very common practice among the researchers like us, to use the heat transfer fundamentals. And as you can see here, that from did I get this equation? From the fundamental law of heat conduction in cylindrical polar coordinate. Okay? So whatever you learn, even you may be doing some advanced level calculations, but the starting point will be the conduction theories which will be applied in order to deal certain aspects of heat flow during the solidification process itself. So conduction, convection, radiation fundamentals can be applied, and you can find out that what is the temperature drop, what is the complete solidification time, etc., by incorporating such measured values, which have been tabulated by many investigators and researchers in literature. Very quickly, the last topic that I want to address is the furnace design. And in furnace design also, this is relatively simple problem. Particularly, the objective is to retain heat within the furnace itself, because generation of heat is expensive. We have to burn, we have to pay for electrical energy, or we have to buy fossil fuels. So therefore, the heat must be contained within the furnace as far as possible. So therefore, if you have a furnace, okay, I draw a cross section of a furnace. This may be, say, a muffle furnace in your laboratory you may have seen. Okay, so you have a refractory lining over it. The task is that I do not want, if this represents this is the steel shell of the furnace. So this is my steel shell. This is my refractory. And this is the space of the furnace. And our objective is that we want this surface temperature as low as possible. That will determine higher is the surface temperature, more is the heat loss. Okay? So therefore, the driving force, because the ambient temperature is 25 degrees centigrade or 30 degrees centigrade, so higher is the temperature. So therefore, that necessitates that we have good bricks or insulating bricks which can contain the heat within the furnace itself. So in the furnace, design of the furnace, and from here to here, how heat flows? The heat flows purely by conduction. So all what we have learned in conduction was going to be applicable. This is the heat flow, thermal resistance, and some certain fundamentals like convective plus radiative heat transfer from the surface, etc. All these things would be needed in order to find out that if you tell me that I want a temperature no more than 100 degrees centigrade when I operate the maximum temperature at 1600 degrees centigrade, you design, you tell me that what should be the thickness of the bricks that I should be using and how the bricks are going to be laid up. You must understand here that it is obviously, it is apparent that the moment you say, sir, what is the big deal? I will use a very thick brick. But if you use a very thick brick, what is going to happen to the furnace volume? The furnace volume will shrink up to this small level. Okay? And if you use too much brick, okay, in order to fulfill this requirement of 100 degrees centigrade at the surface, then you will be buying more refractories. Okay? So that may not be desirable, and the weight of the furnace will go up. That may not be desirable. You can imagine all the vessels in metal industries which has a capacity of 100 ton, 200 ton. They are lifted by cranes and taken to the different locations. And if their inherent weight itself is very large, they will not be able to hold large amount of molten steel or molten aluminum per se. So therefore, it is important for us to ensure a good quality brick, and therefore it has to have a good lower thermal conductivity, and then that we should be able to find out. But again, the more insulating the nature of the brick, the more expensive becomes the brick. So there is an economics of the whole thing also. But most important thing here is that you can imagine that if thickness of the brick goes up, surface temperature, this is the outer surface temperature, goes down. So therefore, I would say mass of refractory going up essentially means thickness is also going up and surface temperature is going up. So therefore, you can see that I want to have a less amount of mass, and I want to have also a less surface temperature. So while the surface temperature is inversely related to thickness, lesser is the thickness, the surface thickness is directly related to the mass of the brick. So therefore, we have a problem which we call, this kind of a problem is called really as multivariable optimization problem. There is no one objective, multivariable optimization. Why multivariable? Because I want to optimize both surface temperature and the mass of the refractory, and the mass of the refractory is directly related with the thickness. So I want to have as low a mass as possible, and at the same time not too large a temperature itself. And if you say in this kind of a problem, typically schematically, if you draw the mass versus temperature, so mass of the refractory, suppose you are monitoring a temperature and then you get a graph like this. So which shows that higher is the mass, lesser is the surface temperature. So this is surface temperature. Smaller is the mass, means smaller is the thickness, higher is the temperature itself. And a desirable window of operation perhaps lies here, where the slope changes not very abruptly. Okay? So, but if you want to work it out, first you have to find out that at what rate the heat are flowing through the surfaces. Now basic through the various segments, and you must understand that one single brick is never used because of the same fact that we can use different layers of brick. One layer of brick could be this, the other layer of brick could be this. They could have different thermal conductivity, and this can be filled up with different non-conductive materials like asbestos, okay, like glass wool, etc. So therefore, you have a series of thermal resistances here. Shell, solidified shell, this is the solid shell, the furnace shell, which is made out of steel. Then you have one layer of refractory, so there is a refractory steel contact resistance here. Then you have a refractory and glass wool, which is in between. So you have now several resistances working in series, and earlier you would have just one, refractory brick, one contact resistance, one steel, but now you have replaced it by a more number of thermal resistances by introducing one contact resistance here, another contact resistance here, glass wool resistance here, and then another refractory resistance. So more number of thermal resistances in the path of heat is being introduced, and that we all know, and that can impede the rate. So in the design of the furnace, we require extensive knowledge of conductive heat transfer. We require extensive knowledge of the thermal resistances, and then of course in the ultimate design we require to carry out that, well, we have found out how to minimize the refractory thickness, minimize the heat flow, and we have to carry out really at the end a multivariable optimization by considering the relationship of mass with thickness and surface temperature with thickness, and then work out that what is the most possible or plausible thickness of the refractory brick, which will meet the objective of 100 degrees centigrade at the surface temperature. So extensively one works out the conduction, theory of conduction heat transfer in the design of the furnace, okay. And as I said, that if you are not concerned with even just optimization, if I say that, look, I want to have this as 100 degrees centigrade, I give you 3 materials and you construct me, a furnace which will allow me 100 degrees centigrade. So you can apply, given that furnace temperature is 1600 degrees centigrade. So various permutation and combinations you can take 2 refractories of certain thickness vis-a-vis 3 refractories of certain other thicknesses, and then you can work out that what is the minimum thickness necessary, which will give you ensure, simply by applying whatever you have learned from the conduction theory itself. Okay? So given brick material to you, different brick material, their thermal conductivities to you, and given an objective that for a given inside temperature, if certain fixed outside temperature is desirable, one can work out by conduction heat transfer theories that what should be the thickness of the refractory lining, whether they should be sandwiched or not, in order to fulfill the objective itself. So we have a series of I think 2 problems based on this, which is done in the tutorials, so that together with this discussion can leave no doubt in your mind that indeed in the design of refractory lined furnaces or refractory lined ladles or other vessels, the conduction theories can be applied to a significant extent. So we have finished our discussion on conduction heat transfer. So next class onwards we'll start discussing on mass transfer, and we'll talk about diffusive mass transfer, convective mass transfer, and in convective mass transfer we will address a special topic which is very interesting. This is the 2 fluid mass transfer, and also we'll do some simultaneous heat and mass transfer problems or cases, and then finally, just like the way we have done heat transfer, we'll do mass transfer, application of mass transfer theories to industrial problems.